video, I'm going to discuss all the labs that we've done over the last couple of weeks. And my main goal is to reframe this and make sure that we have all the tools in our toolbox needed to address our sludge separation. So, let me start off talking about the density of regular solids. Remember, we use these cubes to determine density. We measured the mass by placing these on a balance, and then we measured the dimensions. We measured length, width, and height of all of these, so length, width, height. And we calculated volume based on that. We also did some cylinders with pi r squared h. So once we found densities, we then used a known table, a table of known values to determine the identity of that solid. So that was our density of regular solids. Now, when you're filling in your what you learned column, I don't want to hear like I had fun in this lab, but I also don't want to hear I cured cancer, because you didn't. Like, it's okay to say I learned how to use a balance, or I used how to read a graduated cylinder, or something like that. You don't have to change the world with every experiment, but also tell me what you learned. Don't tell me, boy, this lab was fun. I had fun moving things around. So if at any point you need to pause this and fill in your table and then resume, I think that would be smart. So density of irregular solids, remember we used rocks for those, and we used the displacement method to determine the volume. Once again, we just measured the mass on a balance, and then we used the displacement method to measure volume. Again, we used a table of known values to determine the identity of the substance. So two different strategies for determining density, both used the same kind of end strategy of using a known table to determine the identity. So again, in terms of what you might have learned, maybe the displacement method, maybe how to read a graduated cylinder again, something along those lines. Our next lab was Kool-Aid Concentration. I stole this from a student that submitted it last year. They did this lab a little bit differently. They did them from home. So you can see they used, I'm not sure what powder, what solute they used here. But you see their results. The one that had the lowest concentration was the lightest in color. And these guys were home, so they taste tested this drink, and they said that this was the worst tasting. It's not in these results, but it's there. Then the middle one had more saturation, so it was darker, and it had a stronger taste. And the last one had the strongest taste and the darkest color, which makes sense. The higher the concentration, the more flavor you're going to get out of it. So again, comparing that back to real chemistry, the higher the concentration, the more it's going to do what it does. So if it's really highly concentrated Kool-Aid, it's going to taste a lot like Kool-Aid. If it's really highly concentrated acid, it's going to be a really strong acid, relatively strong acid. We'll talk about what that means. Strong and weak acids have specific definitions in chemistry, so I need to be more careful not to step on my tongue a little bit. But one thing I wanted to point out, we did make known concentrations, but the strengths of our dyes made differentiation difficult this year. So the results weren't quite as dramatic as they are in this picture or as what I've seen in years past, and we've talked about why that might be. So saturation point, remember, it was the second Kool-Aid lab we did. We took room temperature, we took cold water, and we took hot water, and we tried to reach the saturation point. So that solubility is what we were measuring, or I'm sorry, that's what we were calculating. We were calculating how soluble this solid is. Once again, once we determine the solubility, we can use known values to determine its identity. So again, same kind of strategy going on there, just a different way to get to it. And you see the results there. This person got up to 47 teaspoons in the hot solution, only 9 in the cold. So as you increase temperature, you increase solubility. We talked a little bit about how we could use this solubility to determine identity of pollutants in our sludge. But I also mentioned that that's one way that pollution gets exacerbated. If a company dumps polluted hot water into a river, that water is going to absorb more of those toxins and carry them downstream, versus if they pollute cold water, or if they pollute with cold water, then they will end up with those toxins not dissolving into the water and just sinking to the bottom. So trying to reframe this as much as I can on that sludge. Last but not least, I quickly want to go through distillation. We haven't done this lab, and we may not get to do this lab. I may have to come up with a separate way to do this in our 2020 environment. So a distillation is one of the ways that you can separate two liquids. Again, I'm hoping I can model this at least. And what I'll do is I'll have a solution in here that has two things in it. One that boils at a lower temperature than the other. I'll reach that boiling point, and some steam will go up into this tube. It's not set up exactly like this, but this was a close picture I found. And then the steam will go down this cooled condenser. Our condenser will have ice packed around it, and then that will cause the steam to phase change back to liquid, and then the liquid will drip out right here, and we'll have two pure liquids, one here and one there when we're done. So that's distillation. Like I said, procedure is reach boiling point of liquid 1, let it condense. And that's pretty much it. And then what you might learn is this is a way to separate two liquids. Again, I know this is, hopefully we'll get to model it. You haven't learned a lot from distillation yet, but you will soon, hopefully.